So here we are at Secomak, and this is the company that's showing here the range of products of impellers that they have, and some of them are quite different. So you can see different impellers. This other one is one we balanced, and then we have these ones. Okay, and you can see the wide range, and these all go into this type of blowers. Okay, so putting there some
a little bit of oil.
Yes. Okay, to reduce friction.
As it's a soft bearing machine, it doesn't have rollers.
Yeah.
So it requires some lubrication on the nylon slides, if you like, nylon bearings. Can do. Right, okay, we've got a position. So what are we reading there? About 70 on the 100 scale. We're reading 74, nearly 73, 74. We've estimated the weight from the output on the meter. A weight 1.9 grams approximately, and the correction position is at number 7. So we apply that. Now we was reading 73.
Yes.
And we'll see what we're reading now. So we'll check that and see what we get once it stabilises.
Oh, so we are reading approximately the same amount.
Approximately the same amount. So that's indicating that the same amount, but it's now saying number 3, position 3, which is opposite 7, which I can show you that. So there's number 7 and number 3 is opposite. So what that's telling me is I've applied 2 times the correction weight that I should have. So I'm going to remove half the weight, which I've already taken the liberty of splitting into 2. Then we respin it.
And let's see the reading. Oh,
it's quite low. Yeah. It's not perfect, but so I'm going to come down the scale now. So that brings us on to the 10 scale. So we're quite close.
All right.
I can tell you later what that would be.
So now you would do. You would
per millimeter.
Keep on refining the.
So now it's a refining process. So we're about the right position.
Yeah.
The art of balancing is to actually pinpoint the correction location to get it precise. Once you've got it precise, you can add or take away weight, and then you should bring it down quite quickly. If you're not precisely located, as you start adding weight, you start to push the correction point all around, all over the place. So now a small amount of correction. What are we looking at? Probably, I'm not sure. I think that's probably about 0.03 of a gram.
Oh, it's quite small. All right.
It's quite small.
So this is enough for this impeller to be.
Well, it'll correct it. We'll spin it and see how much better that is.
It improved because the level decreased. It's now under 2.
If we go on to the last scale, so we're on the 3 scale technically.
Yeah. So this means 3. We multiply the number that is there by 3. Is it?
Well, what it means is it just means that the amplitude of the signal on the 3 scale is reading about 1.5.
Yeah.
So for us, that's a lot better than the tolerance. The tolerance would be about 3. Here we have a horizontal wide beam laser. We use that to accurately pinpoint the opposite side of our correction weight, because where we've added the weight, opposite to that is the heavy side. which is why we've added weight here. This is the heavy side, this is the light side. We've corrected it by adding weight. What we now need to do is remove the weight from the heavy side so we no longer need the plasticine. And that gives you your drill point. Right, okay. Just making sure I don't drill too deep. We like to save about 1 millimetre wall thickness, but so the rotor doesn't explode at high speed. I can either drill 2 symmetrical holes adjacent to the main hole, or I can drill a hole beneath it. The further away from your centre correction point you go, the less effect it has on the correction. Similarly, if you drill nearer the centre, it has less effect. But what I'll do in this case, I'll drill 2 small adjacent holes.
It must be just 0.05.
We're going to spin it and see what the outcome is. It may need further correction, or it may be good to go. Our tolerance was 2.5, so anything below 2.5 I think I would be happy to call that 1.5.
Yeah, 1.5, because we have 0.5 and the scale is 3. So multiply this number by 3. So yeah, 1.5 to maybe 1.8. The static balance consists in placing the impeller in this rig, and now if I rotate it to a certain position and I release it, you'll see that it will naturally spin, and it is aligning in itself with a heavy spot. And I have it actually marked there. This is where I will add the corrective weight. So when I add the corrective weight, so you can see, I can just show again, I will release and it will spin until it finds equilibrium, okay, because the heavy spot will be below the axis. So if I add now the corrective weight, which you determined just earlier, let's see what happens when I change position. As you can see, it doesn't move anymore, because now we do not have a heavy spot. Well, obviously I have to, I can't give any inertia. It's not exactly balanced, perfectly balanced, that's why it tends to spin a little bit, but friction helps me proving my idea. So as you can see, I can now change position and it doesn't rotate. If I remove the corrective weight, it will try to find equilibrium. That's it. So just to explain another system which was developed under an MSc project in university by Karzan, who we will meet soon enough. We have here the impeller that we just previously balanced using the other technique. We are going to replace it by another impeller, but now we add here a sensor which is an accelerometer. It's going to measure the acceleration at this direction, okay? And this cable goes through and connects and plugs to this system from National Instruments, which is a piece of equipment we have to acquire signals. So here we can acquire the signal from the accelerometer, and then through a USB connection, it goes into the computer. So we developed a software which will be able to give us an automatic response or quick response in order to know exactly where the correction weight needs to be applied. What you did to the impeller in this technique, there are many different techniques, but in this technique, what we will do is basically we have here 0 degrees, 120 and 270 degrees marked. We are going to do a measurement with this impeller as it is, so this is the reference test, and then we will add a weight over there, another weight over here, and another weight over here. And with the software we developed, it should give us immediately an answer of how much weight do we need to remove and at which position. And as we will see, it's going to be quite accurate in comparison to the previous trial and error approach. All right, so now it's spinning, and now
now you have to run the program.
Okay. By the way, what is the meaning of this? Some of these peaks? Do you have any? Can you probably auto-scale the y-axis, please? Okay.
Yeah.
All right. So, what's the meaning of that peak?
This is the end balance, which is at 1x.
You are determining.
So now I'm determining the amount of the trial weight that we need to put on the impeller.
Okay.
To get the coefficient vector.
And that depends on the grade factor we are.
Grade, balancing grade.
Okay, which is the G amount here.
Yeah.
So let's say G1.
G1.
Yes, I think we can even get better, but
the weight of the impeller as well, and the spinning
yes,
speed or
okay,
rotating speed,
yes,
and actually the radius that we're gonna put the trial weight. Calculated trial weight, which is around 2 grams. Yes.
Excellent.
Now we attach this 2 gram at 0 degree, which is here,
and we run again.
And we run again.
So we repeat the process for 0 degrees,
For 0
120,
degrees, yeah,
and 270.
So now we've put all the data.
So we have first run, which is without trial weight, then trial weight at 0 degrees, 120, and 200 and is it 240? It's 240, I said 270, 240. And then the trial weight 200
200 gram.
200 gram. No, 2 grams.
2 grams, yeah.
But it says 200.
Sorry.
Should it have a
2 grams.
2 grams? Okay. All right, and now
Run.
and it says the position.
Position is minus 41 degree from 0,
Yes.
which is opposite, which is with the
In this case, it's rotating in the clockwise direction.
which is we measure in clockwise direction.
Yeah. And the trial weight is correction weight is 1.19 grams. Let's see if it works. And the amplitude decreased quite significantly in the frequency spectrum. And the value now is 0.004, whereas if we go to the 5-run balancing method just to check the first value, was 0.06, so it decreased around 15 times.
Yeah.